I wish you all Happy New Year. First, please let me give my appreciation to professors and experts and students here. It is your coming that highlights the forum. Thank you. I would also like to thank the expert and guests who will share us their presentations. It is their wisdom that has become the soul and the nourishment of this forum. As you all see that the theme of this forum is connecting the mobile world. So we are here online not only to enrich our winter holiday life. More importantly, we hope that through the communication and exchange between the Chinese and foreigner experts and students today, we can touch the forefront of the scientific research and know what the Xidian students are researching. We believe it will bring academic inspiration to other participants, especially the students who are currently abroad. In order to promote the exchange of views among you, please allow me to introduce all the guests to you. We feel honored that Professor Danping HE and Professor Wei Wang attend our forum as keynote speakers. The first speaker is Professor Danping HE. She received a bachelor degree from Huazhong University of Science and Technology in 2008 and a master's degree from the Catholic University of Louvain and the Polytechnic University of Turin in 2010, and a doctorate degree from Polytechnic University of Madrid in 2014. In 2012, she was a visiting scholar in French National Institute for Research in Computer Science and Control. She worked in Huawei Technologies from 2014 to 2015 as a research engineer. From 2016 to 2018, she was a postdoctoral research with the State Key Laboratory of Rail Traffic Control and Safety, Beijing Jiaotong University, where she is currently a professor. Danping, please shake your hand to our audience here. Thank you. Thank you. Well, the second speaker is Professor Wei Wang. He received a bachelor degree in communications engineering from the University of Wuhan in 2003 and a master degrees from the University of Kiel, Germany in 2006 and doctorate degree from the University of Erlangen, Nuremberg, Germany in 2014. From 2007 to 2018, she was a scientific research staff member with the Institute of Communications and Navigations in German Aerospace Center. He is currently a professor with the School of Information Engineering of Chang'an University, China. Professor Wang received the Best Presentation Paper Award in INGN SS 2012 and the Best Paper Award in UCAP 2018 and COTA 2018. He is an associate editor with the IEEE Microwave Antennas and Propagation. He served as TPC members for ICC and VDC conference and workshops. Also, Professor Wang, please shake your hand to all the audience here. Thank you. Thank you. Also, I would like to introduce the sharing speaker that we invited today. They all study at the School of Telecommunications Engineering of Xidian University now. They are Mr. Agnate, a Yemeni master student under the supervision of Professor Li Qiangzhao, and Mr. Wen Xuanlong, a Chinese PhD student under the supervision of Professor Rui Chen, Mr. Manzur Malas, a Yemeni PhD student from under the supervision of Professor Rui Chen too, and finally Ms. Li Jingzhu, a Chinese PhD student under the supervision of Professor Hua Xigu. In addition, our staff member Xin Yue Li and Wen Hui Li, two beautiful girls from the Office of Admission and Quality Assurance Office in School of International Education, are also here with us online and will chair part of the event. Thanks for their work to bring us this wonderful event. I won't hold you up any longer. Let us have our experts start sharing their wisdom. Welcome. Danping, it's your turn.
Okay, so let me share my screen. Okay. Can you see my screen now? And my
Yes,
slide?
it's clear. Yes.
Okay. Hello, everyone, and thanks for the introduction. Today, I'm going to introduce high-performance ray tracing channel modeling for 5G and beyond wireless communications. And this is a tutorial. And I hope through this tutorial, you can understand the principle of ray tracing-based channel modeling and learn how to use ray tracer to simulate propagation channel for mobile communication scenarios. And maybe in some terms, it will inspire new ideas on developing new algorithms and doing researches on radio propagation. And as you may know that there exists multipath propagation in the real environment. For example, the signal between the transmitter and the receiver may exist the line of sight propagation, which we call direct path. And if there are some obstacles, there will be reflection and transmission. If the surface of the objects are rough, there will be scattering. And at the edge of the objects, there will be diffraction. And well, this is the real case. For example, in high-speed scenarios, at the left figures, you can see that, imagine that in the high-speed autonomous driving scenario and the high-speed train scenarios. They are all high-speed scenarios with various environments and with also various configurations and mobility. And the figure on your right side is the MIMO scenario. Well, as you may know that MIMO is the key technology for 5G and also for 5G beyond. And in order to model the MIMO scenario, you may need extensive MIMO channel measurement, right? But this will maybe a very challenging thing because if you need first of all, the MIMO antenna, and you may need a lot of time in doing this measurement, and you require a lot in the surrounding environment. For example, it should be stationary and without any mobility, and so that you can guarantee that all the antenna elements are experiencing the same channel propagation. So measurement, although it's the fundamental of the channel modeling, is useful, but also challenging in 5G and beyond, especially for high speed or MIMO scenario. So we propose that deterministic channel modeling can be used in combination with measurement to dig more information with more configuration. And later on, I'm going to introduce more details on this idea. Secondly, in network planning for specific environment, it needs really accurate 3D coverage prediction. For example, the figure at the left, it shows some ideal base station deployment. It's quite ideal, but what's the real case is that for example, in this urban city, the 3D coverage in the real world is irregular. It will suffer from the obstacles and from reflection and transmission and diffraction. And at the end, the propagation, as you can see, is like this. It's quite irregular. So we will also need irregular base station deployment. So in the real world, in the real engineering problem, network planning in the specific city or place or campus, it will require accurate practical 3D coverage prediction. So digital map-based deterministic channel modeling is more suitable for this task. So we have some motivation to provide a channel model for 5G and beyond communications. And so the channel model for this kind of communication should satisfy the following 3 items. First is to support moving scenario, including the mobile scattering objects. And secondly, it should support MIMO channel simulation. And thirdly, it should be high efficient, meaning that it should have a trade-off, or it should guarantee accuracy and efficiency at the same time. So it's a really challenging work. And as today we propose to introduce the ray tracing method. So let me first introduce the ray tracing theory and the methodology. A ray tracing simulator normally requires inputs like geometric input and the electromagnetic parameters of the geometric objects. For example, what's the permittivity and loss tangent for concrete, for glass, and for brick, and so on. So we should define both geometry and electromagnetic properties at the same time. And for the radio link, we should define the source and destination positions and their antenna patterns. Also, we should define the frequency, the carrier frequency, and the bandwidth they use, right? So the environment and the radio link together are the key inputs of the channel model. After we have all the inputs prepared, we can trigger ray tracer to calculate the rays, the multipath components, and to calculate the field, the electric field. So the output of the ray tracer will include the receive power at the receiver, also all the information of the multipath propagation of each ray. So with this kind of information, we can further derive more channel characteristics. For example, the delay spread, angular spread, shadow fading, and also the path loss components for stochastic channel models. And one more thing is that ray tracing-based method is quite time-consuming because you need to calculate all the geometric paths of the multipath components. For example, the reflected point and the scattered point of each of the reflection paths and scatter paths. And this require many computer science region, the knowledge from the computer science region. And in order to accelerate such method, there are many existing methods, such as using the shooting and bouncing method, or reduce the dimension from 3D to 2D. But this, of course, will reduce the accuracy. And we may also use the space partitioning method, or using the hardware acceleration techniques such as GPU or multi-threaded and distributed CPU computing. So all these kinds of methods all have been applied to ray tracing method. And how about the EM calculation? Well, at the receiver, the multipaths are superposed at the receiver. For example, this is the expression of the channel transfer function. And it's an accumulation of the multipath components, including the amplitude and the phase, and of course, the antenna gain at the transmitter and the receiver. So let's see that how does the antenna pattern have impacts on the multipath components. For example, we have two directive antenna which have a narrow beam width. So if they are pointing at each other, this direct path can be enhanced, right? So you may imagine that what if the antenna patterns are mismatched, are misaligned? For example, if this receiver is rotated with the main beam pointing at other direction, and this direct path will be reduced, right? So the antenna pattern will influence on the path gain. And in order to obtain the channel impulse response, we can do the IFFT at the frequency domain. And at the time domain, we can have this expression. And its equation is boring. And we can see this figure. It's a demonstration of the channel impulse response. The x-axis is the delay, and the y-axis is the power. And you can see that there are many peaks, right? There are many peaks. The blue line is the measurement. The peaks indicates maybe valid multipath components. For example, the direct path, the path from the ground, the path from the tracks, the path from the surrounding objects, for example, the trains. And this is how the channel looks like when you are doing measurement. And the research we are doing in our group is to accelerate the ray tracing method, and at the meantime, to guarantee the accuracy. So you can imagine that when the application scenario become large and become complex, the computation complexity will increase, because we have many surfaces to detect, right? And we have a large scale to compute. So this all will increase the computational time. Besides, we have many different material in the real scenario. These are some examples. We have concrete, red brick, cement, metal, glass, granite. We also have trees, right? And the human body and the cars. All these different materials will make it difficult to determine the propagation model, I mean the coefficients of the propagation model. Moreover, we have various frequencies for 5G and beyond, from sub-6 gigahertz to millimeter wave, even terahertz. Note that the electromagnetic property of different material behave different in different frequency bands. So with all these conditions together, we are facing many challenges. And how can we guarantee the efficiency and the accuracy? I will give some brief tutorial tonight, and maybe inspire you for the future research and future study. So first, let me introduce you the cloud-based high-performance computing ray tracing platform we call CloudRT. In our lab, we have a high-performance computing platform. It was built in 2017. It has 600 CPU cores with 1.8 terabyte memory, and the very big storage, and the peak power of computing is like 14.70 flops. And based on this hardware architecture, we develop the cloud-based ray tracing platform. The architecture is indicates in this figure. As you can see at the bottom of this slide. Well, at the UE side, we call UE is short of user equipment. The UE will access the CloudRT via internet. At the server side, we have web server to receive the requirement from the UE. And we also have managing node to control the simulation and control the behavior of the user. And besides, we have the CPU and GPU-based computing nodes, which have the ray tracing simulator installed. And once the ray tracer is triggered and the simulation is finished, we have all the simulated results stored in the data storage server. And this is the basically how the system works. And afterwards, all the data can be downloaded through the backward direction to user and for further research. And we have already make this CloudRT platform public access. You may visit this website and doing your simulation for your future study. And by simply clicking the CloudRT button, you can access our simulator. And right now, the CloudRT can support various scenarios. It can support mobile scatterers. It can support large frequency range from sub-6 gigahertz to 350 gigahertz. And the propagation mechanism, including the direct path, transmitted path, reflection, scattering, and diffraction model with calibrated EM parameters. It can also support antenna arrays with specified beamforming technologies. We also provide some toolbox for your convenience. And this is the workflow of this, how to use the high performance CloudRT. And at the user equipment, the user normally configure the simulation project through MATLAB and start the simulation in our CloudRT, and then obtain the simulation results through internet and doing further data analysis at the user end. Besides at the cloud, we have 3 libraries, including the environment library, antenna library, and material library. So when you download all the data from the CloudRT platform, you can have many detailed parameters for each ray, including the types, for example, the directed, reflected, scattered, and diffracted type. And if it's a reflected path, you may have the reflection order. And for each ray, you can have the time of arrival, the traveling distance, the field intensity, the path loss, the angle information for each ray. With all this information, you can calculate many channel characteristics. For example, the loss fading, power delay profile, angular profile, Doppler spectrum, and also have some statistical evaluation on the polarization. This is the example of the trace array in the tunnel. And these are some further results we can obtain from the ray tracer. And as I mentioned before, there are 3 libraries. The first one is the environment library. We provide many environment models, including the indoor and outdoor, and also train environment models. You may freely download from our website and doing your simple case study. But for further more complex studies, you may reconstruct your own scenario. For example, you want to do some IoT environment in a smart factory, and you may need to do the reconstruction by yourself, or maybe later you want to do some channel simulation on the autonomous driving scenario at the urban street, and you may need to reconstruct yourself, or SketchUp can provide some third-party models that is also very good to use. And this is some examples. Second library is the antenna library. Currently, we not only provide some basic antennas like dipole antenna or omnidirectional antenna. We also provide some MIMO antenna with beamforming technologies. And we also provide a small toolbox for you to generate the antenna patterns. So maybe for your further research, you can take advantage of this kind of tool to simulate your own channel. This is some examples on how can our small toolbox can be used to generate different antenna patterns for different antenna arrays. And the third library is the material library. And currently, we have like more than 20 material parameters. However, these are not all the material we can find in the world, right? So maybe later, for your own use, if you can find the material in your scenario, you may look up the ITU's reference, or you may need to measure the EM parameter by your own. But anyway, it provides a good example for you to start to begin your channel simulation. Well, I finished the first part on introducing the high performance ray tracer architecture. And then I'm going to introduce you how to guarantee the accuracy of the simulation. Well, in order to guarantee the simulation, we need to guarantee the reliability of the material parameters, right? But how can we guarantee the accuracy of the material parameters? First, we can have some reference from papers. They provide the permittivity loss tangent of different kinds of materials. For example, the glass, the concrete, and some plastic material. And you may also look up ITU reference, as I mentioned. They also provide some materials. But what if we can find useful information from the existing publications? What we can do? What we need to do is to do the calibration, to do parameter calibration. Well, there are normally two kinds of calibration methodology. The first one is to calibrate the material property from the propagation mechanism measurement. The second method is to derive the parameter from real channel measurement in the real scenario. I will briefly introduce these two methodology. The first method we call propagation mechanism measurement and parameter estimation for material. In our lab, we establish a platform to measure the material properties. For example, you can see this figure, right? We have the material mounted in the middle of the platform, which can be rotated by a rotator. And we have the transmitter can be rotated, but we fix the receiver at the other end. And we connect the transmitter and the receiver to the VNA. And by controlling and synchronizing the measurement, we can measure what? We can measure different outputs, different incident angle and different incident angle. And with this different geometry configuration, we can obtain different response from the measurement, from the materials, right? And by replacing the material in the middle, we can measure different type of materials, as many as we can measure. And the figure on the right side, you can see is the other materials we measured already. For example, metal, brick, marble, granite, and nylon glass and organic glass, different kinds of glass. We rotate the transmitter and the material in order to measure different incident angle and scatter angle, and then we obtain the S parameter. As you can see that they are curves, right? They are curves, and the S parameter varies with incident angle and the incident angle. And by fitting these curves with the scattered model or reflecting model, we can obtain different parameters for different models. And this is the workflow of the second method. It's channel measurement-based method to calibrate the materials. Why do we need the second method? Can anybody know that? Because it's sometimes impractical to obtain a material from the real scenario. For example, the decoration of the buildings. They are quite unique and vary from city to city, or from place to place. So we can, well, it's impractical to obtain all different type of materials to our lab or to your lab to measure. It's very hard work, but in this case, we can use the channel measurement method to calibrate the material parameters for the real scenario. And this can also make sure that the ray tracer work in this type of environments. So how this work, how the workflow looks like, as you can see in this figure, from the channel measurement, and if we model the environment, we can start the ray tracers to simulate. And by comparing the measurement with the simulation result, we can adapt the parameters of the materials. And by redoing the simulation again, we can again compare whether we obtain better result or worse result. If it's better, we can further select the material parameter at this iteration. And after many iterations, we can have a very good result, and this algorithm will converge at the end. So this algorithm will return the best parameter values for the ray tracer. I taking one example. We have a channel measurement conducted in the viaduct scenario at 93.2 gigahertz. As you can see that this is a SketchUp of the real environment. The receiver antenna is mounted on the train, and the transmitter antenna is placed at the side of the viaduct. And this is the 3D environment model we reconstructed by using SketchUp. And the right figure shows different results. The blue line is the measurement result. And the dark line is the simulation result after calibration. You can see that after calibration, the simulation results and the measurement matches well with each other. And this green dashed line is the free space path loss model. You can see that how different it is compared with the free space path loss, but with this channel measurement based calibration method, we can calibrate the material properties and parameters for this kind of scenario and have very good simulation results. And after that, after we obtain practical and reliable EM parameters from the measurement, from the channel measurement or from the material measurement, we can apply the channel simulation for various environments. For example, we can extend the scenarios by adding moving vehicles with different speeds. And we just conduct a pure simulation in the virtual environment. As you can see that the channel simulation for this kind of scenario can reflect the real mobility, the influence of the real mobility of the different scatterers. And we can see clearly the loss propagation and unlost propagation. We can see clearly how the rays propagate in this kind of environment. And the second application I want to demonstrate is the MIMO channel simulation. In this case, we configure the antenna pattern as this format is a 4 by 5 to 25 array. Well, it's up to you, the antenna size. And we configure different small base station along the street, and with the channel simulation for each antenna pairs, we can apply zero forcing beamforming to estimate further results. For example, the data rate at the end. So how can we use RT? How can we use the ray tracer simulation for link level analysis? Well, this is the last demo. We show this example shows how the RT can support moving scenario. As you can see that in this environment, there are many vehicles moving along the street with different speed and with various types. For example, you can see a bus and small cars, right? And you can also see that this is the transmitter and this is the receiver which is moving along the street. And the orange color are the scatter paths, and the blue lines are the reflective paths. And sometimes there are loss propagation, and sometimes there are not. And this is the demonstration of how we should we support the moving scenario. Okay, and this is another example on the campus. I think I already exist half an hour, so let me finish this very quickly. So in conclusion, the principle of the ray tracing method is introduced, and the design of the high-performance ray tracer platform is presented, and the application results of the ray tracer for 5G and beyond presented as well and analyzed a little bit. So for more details, maybe we can discuss more offline. And if we have some questions, you can feel free to ask.
Thanks, Danping. It is very impressive work, and we all benefit from it. Now, we enter the question and answer phase. Any audience who have questions can feel free to open your mic to talk to our speaker. Well, you have to notice that Professor Danping is a very famous expert in this research field. So you need to grasp the opportunity to discuss with our speaker. All right, I think there
I
are
have a
more
question.
questions in the dialog box. Danping, we need to check one by one. Is that okay?
Okay.
I have a question that I want to ask.
Aye, okay. Go ahead.
For a MIMO system, we know that there is computational complexity, which is proportional to the number of antennas, combinations when the ray tracing method is applied to MIMO system. Is there any new techniques for reducing the calculations of complexity for MIMO propagation channel estimation?
Well, maybe we need some hybrid method. I mean, for example, if we can use ray tracer to simulate some of the antenna elements in this array, and we can use some super pixel technology, I mean, to up sample the channel. For example, we know the correlation relationship between each element, and then we can easily apply those correlation relationship to different to the neighbor elements, so that we can reduce the reduce the usage of the ray tracer, and we can also have some practical results for all the antenna elements in the array. So this is the first idea I can imagine.
Okay, I got it. Thank you so much for the explanation.
Thanks. Any more questions?
Yes.
Please.
As we have seen two methods, I just want to know about which method is more efficient in clouds.
You mean the calibration method?
CRT.
I'm not sure I understand your question clear. I introduced two calibration methods. Did you mean that?
Yes.
Well,
These two methods, which one is more efficient?
Which method is more preferred by us, right?
Yes.
Yes.
Which more method is more efficient?
More efficient. Well, I think the first method is more efficient because it's more detailed and you know what exactly you are measured. But for the second method, you need to first extract the multipath components from the channel measurement. I mean, if you remember the first figure I showed, this is the channel impulse response we obtain from the measurement. As you can see that there are many peaks indicating that there are many multipath components. And you should analyze which components belongs to which objects. For example, these peaks are from checks. How do you know that? You should dig more information, combine with the geometry information of the environment, and so that you can have the right answer, and then you can reconstruct the environment accurately, and then you can have the geometry information of the rays correct, and then you can calibrate the EM parameter of each ray from the material parameters. So according to my experience, the first method is more efficient and is more preferred. But we can collect all the material from the real world, right? So this is another option. So we have to use it sometimes.
Yes.
Mm-hmm.
Great. Any more?
Yes. On
Hello?
yes.
Yes,
Can you
it's
hear
clear.
me?
Yes, clear.
Okay.
Go ahead.
On which parameters we can compare these two methods with each other?
Well, this is a very good question because it's very difficult to compare them. If you want to use material-based, the propagation-based method, it means that you may not have the chance to do the channel measurement. If you choose the second method, it means that you may not have the material in your lab, right? So it's a very rare chance to compare both methods, but you can, we can choose a very deterministic environment with some common thing materials. For example, the plastic, the concrete, or a simple indoor environment. And we can obtain the material which is exactly the same as the indoor environment. And we can do the channel measurement in the same environment. And then we can compare them fairly. But in our research, we didn't have this chance to do so.
Yes, very, very hot topic. We still have a
Thank you much. Thank you so much.
Thank
Okay,
you.
no problem.
We still have several minutes for the last question. So any more? I think there is so many questions in the dialog box. Student, both from Chinese and foreigner students, have questions to discuss with you. Due to the time limit, I think you guys can discuss offline. All right. Let
Yes.
us thank Professor Danping one more time. Wish you Happy New Year. Thank you.
Thank you and Happy New Year.
Thank you. Next, we will move to the